right, so far so good, I think. All right, so welcome back, and this is just a continuation of Gen Chem 1. So we're starting in chapter 13. So the syllabus has the usual information on it. Labs, the 1230 lab is full. There is room in both the 815 lab and the 320 lab if you would like to switch labs. I know there are some that have biology, and so they're in the morning lab. So if you have that issue, you're going to come at 8:15, start your lab. Then at 9:15, head off to biology, go to biology, come back at 11:15 and finish the lab. If there are any spots that open up at the 12:30, I will let those people know. There were 2 spots left last I saw in 320, and there's some people in the 320 going to 8:15, so I know there's spots open at the 320 slot as well. My office hours are before this class on Monday and Wednesday, 10 to 12:15, and Tuesday 9:30 to 11. Okay. If you have questions on homework and you don't want to come visit, we could also do those. You might have to send me an invitation, but anyway, I just use the WebEx if that works. It works for me. We can meet through WebEx, and I can work the problem on the computer for you. The COVID rules are still in effect. Make sure you have your mask on whenever you are in chemistry, anytime you're in any building at QU. But for sure, when you're in your chemistry class, make sure you have your mask on and you're wearing it properly. I sent out the email. You do not have to come, although you're taking a chance that I'm able to record it. Like this morning, I was not able, and it was working just fine like it is now. And then it just shut down. So I can't guarantee that it's going to work and it will be posted, but that is the plan. But regardless, you do not have to come Monday, Tuesday, Wednesday. Thursday is required. Thursday is the labs and exams. Right. So you in lab, of course, you have to wear the mask and you have to wear eye protection, whether it's a shield or safety glasses, whichever you choose. But you have to have both a mask and eye protection. And then when you're taking your test, you have to have your mask on. All right. So the class schedule, we're starting at chapter 13 and going straight through to chapter 20. So we started at 1 and we're going to go through 20, and then once we hit 20, we do a little jumping around. So after 20, we do not do 21. We're not going to do 21. We go to chapter 23, which is organic, and we take an entire exam on just the one chapter on organic chemistry. After that chapter, then we go back to 22, and then we go to 24. So the last test is on chapter 22 and 24. And so the only chapter that we're not going to cover is chapter 21, which is a different type of chapter. It's more of where do we get our chemicals from. Homework is different. A lot less homework, which also means a lot less points for homework. So instead of the 50 points per chapter, it's 50 points per exam. And so you have 300 total points for your homework. LV2, there's a lot less work on LV2. It is only the EOC for 15 points. The other 10 points are going to be assigned from your textbook. So you should have a physical textbook to carry. If you don't, go to the bookstore and get one. Unless you only want to use the e-text, then you can use that as well. I recommend having a book that you can hold in your hand. And it should come with a solution manual. Hopefully it comes with the solution manual. If not, I can post the solutions. The ones I'm going to assign are the even numbered ones. They do not have the answers in the solution manual. So if you have number 38 that I assign, if you look at 37, it's the same type of question, but 37 is an odd number with the answer in the solution manual. All right, so again, labs are going to be on Thursdays. Here is the lab schedule. All right, so this week and next week in lab, we're doing kinetics, and that's our first chapter that we're going to cover in this class, chapter 13. First one, we determine the rate law, and on the second one, we determine the effect of temperature on the rate. All right, then we do an acid-base titration, 2 of those, solubility product, complex. All right, so and then the dates are given. Note that organic also messes up the lab. Experiment 16, after 16 we're going to do 18. 18 is a dry lab. What that means is we don't need to be in the lab. It is more like a homework assignment than it is a lab. So it is a dry lab, and it is in organic molecular models that you will do as more of a homework assignment than it is a lab assignment. Our help sessions, if hopefully we get a student instructor, but if not, we have you have tutors that are available through the SSC. So if you need a tutor, go to the SSC and find out who's tutoring for this class. The exams, again, there's going to be 6 exams. 5 of them will be 2 chapters. One of them is the organic chapter. The dates, you should note the dates. First test is February 11th. All right, so that is a long time from now. The first couple of chapters are very difficult. It's going to take longer to go through those. Then the next test is not till the next month, March 4th. Again, the next 2 chapters also very difficult, and it's going to take a bunch of time to go through those. Then things get a little bit easier, and then we're going to have a test every other week after that. So the beginning stuff is a lot of math and a lot of difficult questions. When we get later on, it's going to be a lot of review and a lot of you just memorize it. So not something that you have to figure out. It is something, what you have to figure out is how the heck am I going to memorize this stuff, not how do you do the problem. All right. See. Then the final exam is on Monday, May 3rd from 1 to 2:50, and that will be in this room. I'm going to have to check out Thursday where we're going to have our exams. If this room is available on Thursday afternoon, we will have it in here. I think it's going to be available on Thursday afternoon, but I will double check that. Otherwise, we will do our regular exams in the lab. But the final exam is always in the lecture room. It is in here. Grading scale is the same as it was last semester as written there, and then all the stuff we're going through in all the exams. All right. So you can read through the syllabus on your own if you like, and if you have questions on that, let me know. All right, here's where this morning the whole thing exploded. Let's see if it will work today. All right, I think we got this far earlier. All right, we might have gotten this far. All right, here's the moment of truth right here. All right, well, looks like it's working. All right, I will see for sure when I go through the video and see what this thing looks like. All right, so your PowerPoints are all on Moodle. So you can go through those at your own speed. So anyway, we're going through chemical kinetics. And my pen is supposed to work. It does. All right, great. All right, so chemical kinetics is the study of reaction rates, including how reaction rates change with varying conditions. All right, and so the things that we're going to change on Thursday, we're doing a lab and we're changing our concentration. That is the number one thing that we're going to change. The second thing is we're going to add a catalyst. So what you find when you add different concentrations of your reactants, normally the higher the concentration, the faster the reaction. Sometimes you add more concentration and it doesn't change, and very few times, but it does occur, you have a higher concentration and the rate actually gets slower. We will go through all of those different examples in class. The ones in lab, we increase the concentration, we increase the rate. We're also going to add a catalyst. The catalyst just makes the reaction go faster. It lowers the energy of activation and you get a much faster reaction. We will also do that on Thursday. The others are to change the temperature. All right, so when you change the temperature, you have a higher temperature, it is going to go faster. So the hotter the temperature, the faster the reaction will go. That means a faster reaction rate. Then the last one, which we are not going to do, is a surface area. If you try to burn a hunk of metal and you stick it in a fire, it is going to melt and it's really not going to burn. If you finally divide that, you have very small chunks, and this is fireworks. You can easily burn iron. It will burn in a flame, and that is surface area. All right, so here is our concentration of reactant. So as written here, in certain reactions, the rate of a reaction increases when the concentration of a reactant is increased. In some reactions, the rate is unaffected, and then in very, very few of them, you will get a reaction rate that is actually slower as you add the concentration of a reactant. All right, catalyst was the second one we talked about. The example here is hydrogen peroxide. You buy hydrogen peroxide in the store, it's 3% hydrogen peroxide. And if it's expired, it's not going to hurt you. What happened was it gave off oxygen, and now you just have a bottle of water. And so if you want it to turn into water quickly, you can add a catalyst. For this reaction, a catalyst is HBr. All right, so if you have the reaction, you have your H2O2, and that's going to go to H2O and oxygen gas. All right, to balance it, I'll use a fraction, 1/2 O2. Again, when you're adding a catalyst, you put it over the arrow. All right, so if you add HBr to that, that's, if you show it on top of the arrow, that is showing that it is a catalyst, and that just makes the reaction go much faster. All right, and then it turned brown because your HBr is then oxidized to Br2. So that reaction, your HBr is a strong acid, so you have your Br minus. You have just made oxygen gas, and you're going to need 2 of these Br minuses, and what you're going to end up with is Br2, and you're going to end up with O minus 2. So that is an oxidation reduction, so you can oxidize the Br minus with the oxygen that was made in the reaction to produce bromine, which is the red color. So both of those are oxidation reduction reactions. All right, so temperature was then the third one. So we did reactant concentrations, catalyst increases the reaction. Now we're going to talk about temperature. So when you increase the temperature, you increase the rate of reaction. Your rule of thumb. If you increase the temperature by 10 degrees Celsius, you double the reaction rate. All right, so if you took the reaction and it took 10 minutes at 20 degrees Celsius, All right, so you increase it to 30 degrees Celsius, then it's only going to take 5 minutes. So if it is a 10-minute reaction at 20 degrees Celsius, and we change the temperature, so then we increase to 30 degrees Celsius, run the same reaction, it will only take 5 minutes. All right, so you increase the temperature by 10 degrees, going from 20 to 30. You will double the reaction rate. It's going to go faster by a factor of 2. So it doesn't take 10 minutes anymore. It would take 5 minutes. That is a rule of thumb. That is a lot, not all, a lot of reactions will have this general increase in reaction rate. This is the one we're not going to do, and so here they're showing that if you have a finely divided metal and you put it in a flame, it's going to catch on fire, although I think that's not a metal. It looks more like cornstarch. But anyway, very fine particles are going to be very flammable, and that is all about surface area. So yeah, if you want a reaction, if you want to start a fire and you're starting with these giant logs, yeah, good luck. If you cut them all up and you got oxygen all around them, they're going to burn much, much faster. All right, so surface area also, the more surface area you have, the faster the reaction. All right, so to determine the rate, like we're going to do in lab on Thursday, is we're going to see a color change. So our color change is going to go from no color to a dark blue, like purple. So here they have a color change going from a yellow to a blue. All right, and so we're going to time it. So you're going to have not an antique timer. Everybody has their phone. You put it on stopwatch. You start the reaction. You start your clock, and then you see how long does it take for the color to come to this dark purple when we're doing it in the lab, a dark blue or a purple color. Then we're going to change the concentration, do the exact same thing, and see how long that it takes. And so what we'll find in our lab is the higher the concentration, the faster the reaction. So if we have a higher concentration, it'll take whatever, 3 minutes versus a lower concentration might take 6 minutes. All right. The units that we are going to always have reaction rate in. So the units are always here. You need to see that this and this are exactly the same. Capital M is molarity, and that is moles per liter. So saying moles per liter second or saying molarity per second, that is the same thing. It says the unit doesn't have to be that because it's always molarity per time. So it could be molarity per minute, per hour. All right, we're going to use per second, if not every time, 90+% of the time, it's going to be molarity per second. It's going to be molarity per time, and seconds is used. When minutes are given, usually you convert it to seconds. But we will have some cases where you don't want to convert everything into seconds, so you would have it in years at some point. But it's molarity per time. The usual time is seconds. All right, so now we have a decomposition reaction. So we have our N2O5 decomposing into NO2 and O2. And when we balance the reaction, we have 2 moles of N2O5 giving 4 moles of NO2 and 1 mole of oxygen in this balanced chemical reaction. So we're looking for the rate. So there are a number of ways to find the rate. There's actually 2 ways. You can look at the reactants or the products. And so if you are looking at the rate, looking at the product. So we're going to have 0 products to start with. We don't start a reaction by adding products. We have no product. And so you can look at the formation of products. That is one way to find the rate. The other way to find the rate is to look at the disappearance of the reactants. So the two ways to do it, you're looking at appearance of products, or you've added your reactants and you're looking for the disappearance of your reactants. So that's how we're going to measure the rate. All right, so if we do have our chemical reaction up here. All right, so if we look for the formation of our products. So the products are oxygen and NO2. And so the formation of oxygen, that is the change in our concentration of oxygen over a change of time. So it's going to be an increase in concentration of oxygen over time. All right, same with our NO2. It's going to be an increase in our concentration of NO2 over a change of time. Now, when we go to our N2O5, that is a reactant, and it is going to be a decrease in the concentration of N2O5 over time. And that's why you have a negative. Anytime you're looking at the disappearance of a reactant, you always have to have the negative in front. All right, so the reason is at the beginning, when we do our oxygen, delta, so remember, delta means final minus initial. All right, and so when we have our O2, our final concentration is going to be whatever we have as our final concentration. We don't know that. We'd have to calculate it. The initial we know is 0. So we don't start with product. So our initial concentration of oxygen is 0. So final minus initial is going to give us a positive concentration. Delta T, change in time. How much time did it take? You don't have a negative time. So you have always a positive number for your delta T. All right, so the same thing for all of your products. The initial is 0. Final minus initial is going to give you a positive number. Now, when you look at N2O5, now you have final minus initial. If you're waiting for this to go to completion, so you're getting the color change when the N2O5 is gone. So now your final concentration is 0. All right. So you started with some amount, whatever. You start with, who knows, whatever you start with, 0.1 molar. Whatever concentration you're starting with. All right. And then it's not going to change a color until it's gone. And so the final concentration is 0. We're looking at a reactant that is going to 0. So final minus initial is always going to give you a negative number when you're looking at a reactant. And that's why it is required to have the negative out in front. All rates are positive numbers. So rate is always positive. If you ever calculate rate and you get a negative number, you did not put the negative out in front. All right, so all rates are positive. There is nothing that will be a negative rate. Every rate is a positive number. All right, so now the next slide is going to show how we make them the same, whether we're looking at the N2O5, the NO2, or the O2. All right, and that's due to the stoichiometry. All right, and so we can relate these expressions by taking into account the stoichiometry. So let's go back here. All right, so I'm going to start with the oxygen. All right, so we're looking at the appearance of 1 mole of oxygen. So the same time that it takes to get 1 mole of oxygen, that same time it gets us 4 moles of NO2. So when we get 1 mole of oxygen, we also get 4 moles of NO2. All right, and so the NO2 is 4 times larger than the rate of formation of oxygen. So what we do is we divide by the coefficient because it is 4 times larger. Instead of multiplying the oxygen by 4, which we could do, we don't. It is understood that we're going to go with the 1 mole and keep it 1 mole and not multiply it. We're going to then divide the other ones by their coefficients. And so since we get 4 moles of NO2 for every 1 mole of oxygen formed, to make them the same rate of formation we divide our NO2 formation by 4. We react, 2 moles of N2O5 reacts to give 1 mole of O2. So when 1 mole of O2 reacted, 2 moles of, when 1 mole of O2 was formed, 2 moles of N2O5 reacted. And so that is twice as much reacted because 2 moles are required to react to give 1 mole of oxygen. Again, so to make them the same number, we have to then divide by 2 the rate of decomposition. And so now all of these values are exactly the same. So you divide by the coefficients of the balanced chemical reaction. All right, dividing by 2, dividing by 4, dividing by 1. Note that dividing by 1 doesn't change this at all, but you are dividing by the coefficients, and now they are all equal. And so we can set up, no, they don't show the other one, okay, which is also equal to 1/4 the concentration of the NO2 over a change in time. All right, so once you have divided by the coefficients, now all of those numbers will be exactly the same number when you calculate them. NO2 is a product. So note the negative is the N2O5. So the negative one is here. So there were 2 products. This one's positive, and this one is positive. The 2 products are positive, so they don't have the reaction here. The reaction is the 2N2O5 goes to, well, I should put it in the same order they had it before. That is your 4NO2 and your O2. All right, so the NO2 is a product, it's going to be positive. The O2 is a product, it is a positive. It is the N2O5 that is the reactant that is disappearing, and that's the one that gets the negative. All right, so now these are all the same because you do final minus initial, your change in oxygen is positive. Final minus initial, your change in N2O5 is negative. That's why you need a negative out in front to make that a positive number. And then, of course, your change in your NO2 is a positive. All of those numbers are going to give you the exact same positive number. All right, so these equations give the, okay, so now what we're going to do is we're going to get an average rate. So if the question is, what is the average rate over a time interval? You're going to simply take the 2 points and you're going to take the change in the concentration and divide by the change in the time. All right, so here are the 2 points that they say give the average rate. So this one is at the 600 second mark, and this one is at the 1200 second mark. So we're looking at the points. They're going to give you 2 points. So right here, the 2 points they give you are the question would be, what is your average rate when you're looking at the time of 600 to the time 1200 seconds? And so all you do is you take your change in your concentration of oxygen, all right, which is final 0.0036 minus initial 0.0021, and then you divide that by your change in time. Final is 1200, initial is 600. And when you do that math, you get the numbers they have here, 0.0015 when you subtract those 2, and 600 when you subtract those, and then you push the buttons and you get your answer. And now this is a rate, it is an average rate, all right, and so the units are moles per liter second or molarity per second. All right, so you can put units as moles per liter second or molarity per second. All right, and now in this case, all right, so we can look at this as what we're doing is rise over run, and we're getting a slope. All right, so when we do the rise over the run and getting our slope, we see that a slope here is a steeper slope, a higher number than the slope would be here. So when we connect these two and we make a straight line and we find the slope here. So these 2 points, we're looking at 4,200 seconds to 4,800 seconds. So now we're looking at the average rate between 42 and 48. And so we put in our numbers and we get 5 times 10 to the minus 7. All right, and 5 times 10 to the minus 7 is much smaller. All right, it has a smaller slope. It is not as steep. It doesn't have the large, steeper slope. All right, and so this is a higher number. And that's a smaller number. And you can see by connecting the 2 points, you have a steep slope here. You have a less sloped line up there. All right, and so they're not going to be the same. The only time they would be the same is if you're looking at a straight line. This has obviously got a curve to it. Anytime your line has a curve to it, when you're plotting your time versus concentration, you're going to have a different slope at the different times. And so they'll ask for an average rate between 2 points. And you simply do final minus initial to find your average rate between 2 points. All right, so now we can do calculus. Everybody loves calculus. All right. So for calculus, we use very, very small delta t's. And so when they say that we're going to talk about tangent lines and we're going to have very small approaching zero, now we're doing a integration, and now we have a dt. So you have your dx usually, but anyway, d anything, and this time we're talking about t, so this is a dt. So now we're talking about calculus. You do not have to understand anything about calculus, but if you do, you can understand this better. You don't need to understand this better to get, you just are going to use what they give you from getting the information from their integrations from calculus. But I will tell you that this is what's happening. You do not have to do the math of what's happening. All right. All right, so this would be an example of relating the rate of formation to the rate of reaction of fluorine. All right, so the NO2F here and then the fluorine here. All right, so this would be a question on a test. This could be a very difficult question. This could be a very easy question. It depends on, well, how much you're going to study. So what we do know is that the rate of formation, that is the change in my concentration of fluorine over a change in time. And we also know that it is a reactant. It is a disappearance of the change in the concentration of fluorine over time. If we're looking at the rate of formation of NO2F, we know that that is going to be a positive because we are producing our NO2F over a change in time. All right, so that's how we would find our rates. Now, we want to then relate the rate of formation to the rate of the reaction of fluorine. So we want them to be equal. In order for these numbers to be equal, we see that 1 mole of F2 will produce 2 moles of NO2F. All right, and so to make them the same, again, we're going to divide by the coefficient. And now, since we used up 1 to make 2, now we had to divide the one that we made 2 by 2. And now we have the same number for our rate. And so that is what they are looking for when they are looking for the relate the rates in a reaction. So we can look at the disappearance of fluorine. We can look at the appearance of NO2F. If we want them to be related, doesn't matter if you're looking at this one or this one, we want you to have the same number, then you'd have to divide by the coefficient from the balanced chemical reaction. All right, this would be the easiest question on the test. Again, only easy if you know what it's asking. All right, calculate the average rate of decomposition. And so when you see this average rate of decomposition, you're simply going to take the change in your concentration over the change in time, and that's your answer. And so they give you 2 points. They're going to give you two. Anytime they say what is the average, they're either going to give you 2 points or they're going to say there's a whole bunch of points. What is the average between these 2 points? So the average is always between 2 points. Here they only give you 2 points, so that's the 2 points that you're looking for. And so you have your final concentration, 0.93 times 10 to the minus 2, minus the initial concentration, 1.24 times 10 to the minus 2, divided by your final time, 1200 seconds, minus your initial time, 600 seconds, and you simply push the buttons on your calculator to get your answer. All right, so, but the numbers that they're giving us are for N2O5, and remember that your rate is always a positive number. When you push the buttons on your calculator, you will get a negative number. All right, so when we're looking at a reactant, it is the disappearance of your N2O5 per time. Now, that's all you have to do to get your average rate of decomposition of N2O5. Now, if it says related to that of the fluorine, then you have to divide by the coefficient. So if it just says calculate the average rate of decomposition, you're simply putting in the numbers they give you and you have your answer. If they then say compare that to, relate that to something else, then you're going to divide by the coefficients. All right, so there is the rate of decomposition of N2O5. All right. Now again, if it says relate that to the formation of oxygen, you would have to then divide it by 2, the coefficient of 2. If it doesn't say to relate it to something else, you do not divide it by the coefficients. All right, and so if you have, again, this is not a straight line. A straight line looks like that. This is obviously a curved line. That is not a straight line. If you get a ruler and you put your ruler between A and B, that is not exactly the same line that they have there. So this is not a straight line. All right, and so what we're looking at, if we're looking at A, we're looking at the line that would intersect A here. And then we would look at the line that intersects the B here. And so we're looking at a line that looks this way and a line that looks this way. All right, so we see that your slope of A is larger than the slope of B. So when we look at our 2 points, we see that the slope at point A is going to be greater. It is a steeper slope. All right, and so the rate is greater at that point, and we see that B is a lesser slope, and so it is going to be smaller at that point. And then your average rates are going to be different between any 2 points because it is not a straight line. If this were a straight line, well, then all the points would be exactly the same. They would have to, then you put your A here and your B here, and you draw a line, and that's what you get. Well, yes, so then your average is going to be the same everywhere. So the only time that the average is going to be the same everywhere, which is your slope is the same everywhere, is when you have a straight line. If you have a curved line, it is not going to be the same at the different points. All right, so rates are determined experimentally. All right, and so we're going to go in the lab Thursday. We're going to change our concentrations. We're going to see how long it takes for the reaction to turn to color. And from that, we can calculate the rate of our reaction. All right, once we find our rate, we are going to then find the rate law. So a lot of points on this chapter is going to be calculate the rate law. All right, and so your rate law is going to be rate times K. K is a constant times the concentration of reactants raised to some power. All right, if you have 2 reactants, you got to list them both. If you have 3, you got to list all 3. If you have 4, you got to list 4. Normally we have 1, 2, or 3. We don't normally have 4 or more. But if you have 1, there's 1 there. 2, there's 2. 3, there's 3. And so K is a rate constant. And so K is a rate constant. Now, I will say it's a constant at a given temperature. If you change the temperature, you have then changed the rate constant K. All right, so on Thursday's lab, we are not changing temperature. Whatever the temperature is in the room, that's the temperature we're using. We're going to write it down. What is the temperature in the room? And so our K values for week 1 are all exactly the same because we are not changing the temperature. Then the following week, next week on Thursday, we are going to change the temperatures. And so the K values would be different. We're going to use room temperature, 10 degrees above, 10 degrees below, and we're going to use an ice bath. All right, and so the K values are not going to be the same for those 4 different temperatures. All right, so K is a constant for a reaction at a given temperature. All right, so here is a reaction. All right, and so here they have, okay, I guess that's true as well. All right, good point. All right, so you have your generic reaction, and C is listed on top of the arrow, which means it is a catalyst. All right, and they list that for you here. Because that is listed on top, it is a catalyst. All right, so your rate law is written as rate is equal to K, the concentration of your reactants. So there's A raised to some power M that has to be determined experimentally. B raised to some power N, and note it is not raised to the coefficients, not raised to the coefficients. And then catalyst. So your rate law includes reactants, it can include catalysts, it can include products, which is very rare, but it can include products. It cannot include a reaction intermediate, which we will get into later. All right, but the normal case of a rate law is rate is equal to K times the concentration of reactants raised to some power. It can also be a catalyst, which is not as likely. It's not that likely to have a catalyst, but it's even less likely to have a product. It is a violation to have a reaction intermediate. All right, so what we're going to do experimentally is find the exponents M, N, and P. Note that in the lab, I use X, Y, and Z instead of M, N, and P. It doesn't make any difference what letters you call your exponents. All right, so we have to do an experiment to find these, and this is going to be a lot of the test, is to interpret these experiments and find your rate law. Once you find the rate law, then you're going to have some very easy questions to answer, and that is the reaction order. So if your exponent M is a 1, so if M is equal to 1, then it is first order with respect to A. All right, and then this has to be done experimentally. All right, so we did the experiment and we found m is 1. So if m is 1, then it's first order with respect to a. If then n is equal to 2, then it is second order with respect to b. All right, and then if p, the third exponent there, is equal to 0, which is likely, then it is 0 order with respect to c. All right, and so then you add them up and you get third order overall. So a first and a second and a 0, a 1, a 2, and a 0. It is a third order overall. So the overall, you just simply add up the reactions. When you have a 1 and a 2 and a 0, you have a third order overall. And so the way you would write that, if that were your answers, so you would write that the rate is equal to K, your concentration of A raised to the first, the concentration of B raised to the second, and you would not put the C, because, I will put it here, anything raised to the 0 is 1. Raise anything, any number, any letter, anything raised to the 0, it is 1. So C represents some concentration. It doesn't make any difference what the concentration is. If you raise it to the 0, it is 1, unless, of course, that concentration is 0. And so if your concentration is 0 and 0 raised to the 0, I haven't done it on my calculator, but that should be 0. Hopefully that is correct. I always say anything raised to the 0 is 0. I don't have my calculator with me. But I'm hoping that 0 raised to the 0 is 0, but there's a little, I've never tried that. So anyway, so C is some concentration, but there's going to be a lot of experiments or a lot of reactions. If you don't have the catalyst, the reaction doesn't occur. And so if you have a 0 concentration of your catalyst, there is no reaction. It's not going to occur. And so 0 raised to the 0 better be 0, or I've got another issue to deal with. All right, so that's how you get the reaction order. Once you did your experiment, all of your exponents, those are your order with respect to each reactant, and then you add them up to get the overall order of your reaction. All right, so here we have 2 NOs plus 2 H2s. That's going to give a nitrogen and an H2O, 2 H2O gases. Now here, note, very important that it says it was already experimentally determined. You cannot come up with this rate law. You can guess a rate law, but again, that is just a guess. We don't guess in science. We do the experiment and we know. All right, so if you're given a reaction and says, what's the rate law, you have to use experimental data, or you go to the lab and you do it in order to find that reaction, that rate law. All right, so this was done experimentally. They gave us the answer. Rate is equal to K, NO to the second, H2 to the first. Again, this is understood. There is a 1 here. You don't put it, but there is a 1 there. And so it's second order with respect to NO. It is first order with respect to H2, and it's a third order overall reaction. All right, so the key here is the word experimentally. You cannot get a rate law unless you do an experiment to experimentally determine the rate law. All right, again, experimentally determined. So this rate law was already went to the lab and experimentally determined. All right, so that's also a multiple choice question. How do you find a rate law? And the answer is you must find it by an experiment, experimentally determined. All right, you cannot use the coefficients of your balanced reaction, because then you would have a 5, a 1, and a 6. And no, you have for bromine, not a 5, but a 1, the bromide ion, that's a 1. 1 for, yes, there you'd have 1 out of the 3, right? And that's not a 6, that's a 2. So So in this case, it's first order with respect to Br minus. It is first order with respect to BrO3 minus. It is second order with respect to H plus. You simply add up your 1, your 1, your 2, and you have a fourth order overall. All right, so it's first order, second order, and fourth order overall. So that's the easy part. The hard part is finding the experimentally determined rate law. It's hard to find that by the experiment. Once you have that, find the orders, very simple. Whatever the exponents are, those are your orders. 1, 1, and 2. And then you add them up for the overall, and you've got 4. All right. So here is a reaction. I think this one is going to confirm I hope so. All right. So here's a reaction. You have two reactants, Q and R, giving two products, S and T. All right. And so the rate law, all right. So this was the experimentally determined rate law. And here it is. All right. So rate is equal to K, Q to the 0, R to the second. Again, if you have a Q to the 0, this is equal to 1. All right, and just like you don't put the 1 as an exponent, you can. Most people do not put the 1. You can write every number you have and put a 1 up there. So not everybody, you don't write whatever, 2.0 to the first and 1.0. If it's a 1, you don't put the exponent. And if it's a 0, you don't put anything, because anything raised to the 0 is 1. Except when they give Q is equal to 0 molar. All right, and so your rate law is rate is equal to K concentration of R to the second. All right, so that is your rate law. All right, so Q to the 0 is equal to 1. But however, the reaction is that Q and R, you have to have reaction of Q plus R. So if you have 0 concentration of Q, you are not going to have any reaction. There is no reaction that's going to go to the right, because there's no Q that can react to go to the right. But as long as the Q value is not 0, any other number, where it's 1 molar or 2 molar, it doesn't matter, because these numbers raised to the 0 are going to be 1. So it makes no difference. But 0 raised to the 0 had better be 0. All right, so I'm going right to the answer. Right, so there's no reaction. So 0 to the 0 has to equal 0. All right, so there you have to have a reactant. All right, so if two reactants are needed, you have to have both of those, or the reaction does not occur. All right, for the one that's raised to the 0, it doesn't make any difference what the concentration is, as long as there is a concentration. If there is 0 concentration, then there is 0 reaction. Again, for the I don't know how many times, rate law must be determined by experiment. So this is what we're going to do Thursday. This is what you're going to have a lot of homework questions on, and that is the initial rate method. So what you're going to do is you're going to be given a concentration and a rate. Then you're going to get a concentration that is twice as much as the initial, and you're going to get a new rate. And all of these are going to be measured at the same temperature. When you're getting the rate law, you do all of your reactions at the same temperature, so that the K value is exactly the same for the first run as it is in the second run. All right, so if you have one reactant, in this reaction, we have one reactant. One reactant requires 2 experiments, and so you have to have 2 experiments in order to find the rate law of a reaction that has one reactant. So just as I said, you're going to run a reaction. In this case, you're going to have 1 times 10 to the minus 2 molar, and you find the rate. So you're looking at the color change. You have the color change until all of it's gone. You put it in the initial rate equation, and you get 4.8 times 10 to the minus 6 mole per liter second, or of course, molarity per second. Note that that is the same. Moles per liter second is the same as molarity per second. All right, so then you can make any initial concentration you want. And so almost everyone, and we're doing this in the lab, are all going to be a factor of 2. Although our first run is with a higher number, a higher concentration, then we dilute it and do it. It doesn't matter if it's twice as small or twice as large, it's a factor of 2. All right, so here in experiment 2, we are multiplying our concentration by a factor of 2. So from here to here, it is times 2. So instead of 1 times 10 to the minus 2, now we have 2 times 10 to the minus 2. And then we have to see what happened to our rate. All right, and we see that when we go from here to here, it also went up by a factor of 2. So your 4.8 to 9.6, you can use your calculator, divide it, and you will see that that is a factor of 2. All right, and so as we doubled our concentration, we also doubled our rate. And so note when you're doing your rate law, rate is equal to K, concentration, in this case of N2O5, it's going to be raised to some power. They're going to use M, I use X, Y, and Z, they use Mn and P. It doesn't matter, again, what the letters are you use. And so that's what we're looking for. We're looking for what is this factor X. And so in this reaction, what we're going to do is we're going to then relate one of those to the other. All right, and so we're going to have what I put, the one on top, is always the higher number. I like to not work in fractions. All right, so I'm going to put the 9.6 rate on top. So that is, I'm going to call rate 2. And on bottom, I'm going to put rate 1. It doesn't matter. If you invert this, you get exactly the same answer, but you're dealing with fractions instead of 2, you're working with 1/2. And so now my concentration, okay, so then it's concentration of N2O5 raised to the power X. And so what I have is my rate doubled. So rate 2 divided by rate 1, that is going to give me 2. K divided by K, K is a constant. We're not changing the temperature. That's exactly the same. And so then we also see that we doubled our concentration. And so rate 2, when we had rate 2, our concentration here was 0.02, and here it was 0.010. And so we know that also went up by a factor of 2. And so that is a 2, but now when you're doing your concentrations, that's when it's raised to the power, and that is your X. And so now you have to solve for X. All right, so that's a very, very easy solution. In lab, it's not going to be as easy. You're going to have the perfect 2 to the X, but your rates are not going to be a perfect 2. They're going to be something else that you're going to have to calculate. So to solve this, all right, if this wasn't as easy as it is here, you would take the log of both sides. And it doesn't matter if you take the log log or the ln log. It makes no difference. I'm going to use ln of 2 is equal to the ln of 2 to the x. And if you remember your log rules, exponents come out in front. So you have the ln of 2 is equal to x ln 2. And now to solve for x, you divide by ln2 on both sides. And so your ln2 cancels your ln2. And so since ln2 over ln2 is simply 1 is equal to x. So you could have in this simple equation said, well, of course, x is 1, 2 to the first is 2. And so now we have the rate law. And so your rate is equal to k N2O5 raised to the first power. So that is your rate law that was determined by these 2 experiments. And so the rate is first order with respect to N2O5, and it is first order overall. Since there's only one reactant, It is not only is it first order with respect to that one reactant, it's also that's the overall order. There's nothing else there. All right, so there will be a lot of these types of questions. It took a while to freeze, but it looks like, did I freeze my computer? No, okay. All right, good. All right, so here is a fast way to get your answer. However, this is only when you double the initial concentration. This only works if you're doubling it. All right, so if you double your concentration, what you need to know is your concentrations have the exponent. So this is all 2 to the x, m, n, o, p, whatever, x, y, z, whatever exponent you're using. And so if you're 2 to the x, right here, so they're using m, oh, fine, m, be consistent with the part. All right, so 2 to the m. All right, so if I doubled my concentration and I doubled my rate, so this is the rate also doubled. This is the one we just did, where we doubled our concentration, we doubled our rate. So then your exponent is 1. If I doubled my concentration, but my rate increased by a factor of 4, then my exponent is 2. If I doubled my rate, but it didn't change the rate at all, I doubled my concentration, but it did not change the rate at all. So I doubled my concentration, but the rate was exactly the same as it was before I doubled it. Then you need to know that anything raised to the 0 is 1. All right, and so if it doesn't change, then your order with respect to that reactant would be 0. And here is the weird one where you double your concentration, but the rate got slower by a factor of a half. And so this is when you can have a negative exponent. All right, so that would be a -1 order for that reactant. All right, so you can use this table anytime you are doubling your concentration. But if you understand the math, it doesn't matter if they triple it. So if they say, I tripled my concentration, and then you look at the rate and it also tripled, you see, I keep using x, all right. You see that your coefficient, your exponent, is going to be a 1. Now, if you tripled your concentration and your rate does not change, then you have a 0 order. If you triple your concentration and your rate went up by a factor of 9, that's when you have a coefficient of 2. 3 squared is 9. So this table is only for your concentration doubling. But if you understand where they're getting their numbers from, it doesn't matter if they triple or they quadruple. You can do the math and figure out the order. All right. So here we have a reaction that has 3 reactants. All right. So if you have 3 reactants, you are going to be required to run 4 experiments. However many reactants you have, you need 1 more experiment than the number of reactants in order to find the rate law. On Thursday, we have 2 reactants, and so we're going to do 3 experiments in order to find our rate law. All right, and so we're going to have the table on the next slide, and we're going to find our reaction order. All right, so here are the 4 experiments. Now I'm going to look at experiment 1 to 2. So from 1 to 2, we see that we doubled our concentration of H2O2. This had no change. This had no change. All right. So we look at our concentration of our H2O2. It has doubled. And now we look at our rate from here to here. It also doubled. All right, and so from that, we know that our concentration of H2O2, when it doubles, the rate doubles, and so that is a first order with respect to H2O2, because the concentration of our H2O2 is the one that is raised to the power of m. All right, and so that has doubled. All right, and so we double that and we double the rate, and so our m is equal to 1. And so we know that it is then first order with respect to our H2O2. All right, now we have to look at, we only want one thing to change. So if we go from experiment, if we look at 2 to 3, so let's say you went from 1 to 2 and now you want to go from 2 to 3. The reason why you cannot go from 2 to 3 is because you are changing your H2O2 and you're changing your I minus. You need 2 experiments, but only one thing is going to change. All right, so now we're going to look at experiment 1 to experiment 3. All right, so here we have 0.01 and here we have 0.01. And so there's no change in my H2O2. The I minus from here to here is doubling. And then this one does not change. So there's no change here. So one thing is changing. So the I minus is doubling. So when I double my I minus, all right, so I'm going to double my I minus. What happens to the rate from 1 to 3? It also doubles. And so now I have n is equal to 1. So I already had the m is equal to 1, and now I have n is also equal to 1. All right, and so now I'm going to go from experiment 1 down to 4. The reason why is I'm not changing my H2O2. It is staying at 0.01. I'm not changing my I minus. It's also staying at 0.01. I am doubling my concentration of H plus. So that is a factor of 2. And so now I need to see what happened from my rate here to down here. We see that it did not change at all. It's exactly the same rate in experiment 1 as it is in experiment 4. All right, so it is simply, whatever, times 1. It doesn't change at all. It's exactly the same. And so you end up with 2 to the p is equal to 1. All right, so we're looking at now our H plus. All right, and so again, anything raised to the 0 is 1. And so p is 0. And so this is going to take a lot of practice. You'll have to do this many times to get familiar with what's going on here. But what you end up with then is your rate law. Go to the next page. So your rate law, what we just determined, is K, concentration of H2O2. We calculated that M, since we doubled the concentration of H2O2, we doubled the rate. That was a 1. We don't need to put a 1. 1 is understood. Concentration of I minus. Again, we doubled our concentration of I minus. We doubled the rate. It is also a 1. And then our concentration of H plus is raised to the 0. We don't put it. Anything raised to the 0 is 1. And so our final rate law from these experiments is rate is equal to K, concentration of H2O2, times the concentration of I minus. So it's first order with respect to H2O2. It is also first order with respect to I minus, and add them up, it is a second order overall reaction. All right, so that is, they're going to go through this in great detail right now. All right, so here is the solution. All right, and so you divide your two rate laws. All right. Now, all of these are done at the same temperature, and so your K values will cancel every single time. Then you plug in your numbers. All right, and so again, these are the same, they cancel. These are the same, they cancel. This is a factor of 2. And so you end up with 2 to the m is equal to 2. All right, so you can go through all of this and you will get the exact same answer. For m is equal to 1. And so it's first order with H2O2. They're going to do the exact same thing for the next one. And they're going to get 0 for the next one. And so your rate law is there, and it's first order, and 0. If it's 0, you can put that it's 0 order, but you don't have to. It's first order with this one, first order with that one, second order overall. But if it asks specifically what is the order with H plus, the answer is 0. It is 0 order with respect to H plus. All right, so then it's going to say calculate K. So when you're going to calculate K, all right, in lab, you are going to do K for the first reaction, K for the second reaction, K for the third reaction. We're doing 3 reactions in lab, and you're going to take an average. You can do that for a problem in the book, except they're all the same. All right, so in the book, it's perfect. K is a constant, and it is a constant. It is exactly the same thing all 3 times. All right, in lab, you're doing the lab. There's experimental error, and so you should get the same K value every time, but you're not going to. You're going to have different K values, and then you're going to take an average. But K is a constant. If you added the exact amount each single time with a pipette with the number of sig figs, you would get the same number for K. We're not doing it that specific, and so you're going to have some differences in your K value. But for the ones here, you plug in your numbers for experiment 1 or 2 or 3, you will get the exact same answer for your K. So in experiment 1, our rate was 1.15 times 10 to the minus 6. K is a constant. We're going to solve for it. And then our concentration for H2O2 was 0.01. The concentration of I minus also 0.01. It doesn't matter what the concentration of H plus is because it's raised to the 0, and it's going to give us 1. And so here it is. You just divide both sides by 0.01, and you have your answer. 0.01 and 0.01, divide both sides by 0.01, and you get 1.2 times 10 to the minus 2. Here they're doing the correct sig figs. All right, you're doing a division. Here's 2 sig figs in this number, 2 sig figs in this number, 3 sig figs in this number, and they're giving their answer to 2 sig figs. I am not that strict on sig figs. If you're giving ridiculous numbers of sig figs, you will lose points, but these problems are hard enough to do without taking points off for sig figs. All right, and we will pick up there tomorrow.